All right. So, welcome to the multi-body space structure course. This course will last from today until the end of May, basically, last week of May. We will have 5 hours of lectures every week. So it's this room, which is room 15, and then room 32 on Thursday and Friday. So it's today from 1 to 2 p.m. and then on Thursday it's from 4 to 6, and on Friday from 2 to 4, okay, p.m. So these are the lecture. Please always proceed to register if you have the chance through Prodigit to book your place. It's just some formalities, but we are we are obliged to do so due to the epidemic condition. And so first of all, you saw maybe that you have already given the chance to follow and to join a group on Microsoft Teams. Okay, so I organized there all the materials of the course. So there will be a folder to where I will upload all the notes, meaning the handwritings at the board, and also the class notes. So I will provide you also with notes, which is basically this one here for those you can see. And at the end of each lesson, I will upload the material. So you will have either the notes, okay, or the handwritten notes on the board, plus the video lecture. Okay, so there will be plenty of references. And all of this will be organized through Microsoft Teams. I didn't yet define office hours for any one of you who want to join and reach me for questions. I'll make sure to define it in the web page of the course, which is in the page of the concealed area, as you saw. So every information will be made available there. Also, the session for the exams are already open, so you can ideally book, okay, already basically from the next one. So right after the end of the course until September, they're already open, so you can book whatever you want. And you will find all the information about the times and the dates of the exams on the web page of the course. All right. So this being said, if you don't have any question, you can start. First of all, I would like to share with you the program of the course, to have an overview. Okay. So let's say introduction. To multi-body space structure course. Okay. All right. So let's see. Okay. It should be one. Okay. So this is. I'm not sure if you can actually see it. Hope so. So this is basically the first. It's basically the index of the notes. Okay. It's just a reference to present you the contents. So we go through today a very quick introduction on the course, which is what we're already doing, and we will see why it is relevant to deal with the dynamics of multi-body structure for space applications. Okay, we will touch different topics, all basically regarding the environments. Okay, the space environment. Why it is relevant in this environment to take into account flexibility. Issues, okay, regarding the structural response of structure of systems composed of multi-body, so multiple bodies and multiple parts, when they are, let's say, placed in the space environment. Then we will basically proceed to start with the kinematic description of rigid bodies. So we'll deal with rigid bodies first, and we will see how we can describe the position of orientation of these bodies in the 3D space, how they can be univocally identified, okay, each point, and described. So this is, let's say, the first part. Then the second part, allow me to introduce it. It's here. So you see, we will be going from the description of the orientation and the position of a rigid body, which is the kinematic of the body, to the dynamics. The dynamics is involving the law of the motion, okay? So the equilibrium equations and the equation of motion of the body. So once we have understood how to describe various bodies, rigid bodies for now, in a 3D space, we will see how to be able to describe their motion, given some inputs and constraints. Okay, so we will implement different formulation. We will go through Lagrange formulation. We will see how to deal with, as I said, with different kind of constraints, holonomic, non-holonomic constraints. We will then go through also through Keynes' method for deriving these equations. And then finally, we will land on the Newton-Euler's, let's say, formalism for this equation of motion. So this is basically the first part of the course. So it's rigid bodies, how to describe their position and orientation, and how to describe their motion. Then, okay, I placed in the notes, in the class notes, a small, let's say, recap of the mechanics of the formable bodies. Okay, even if it's not strictly the topic of the course, okay, because you already, for sure, have gone through this topic, okay? You already have seen all the, let's say, formalism to describe the stress and strain, okay, in a rigid body, in the formable body, always keeping, let's say, a point of view of linearization. So everything will be linear in terms of the description of the state of stress and deformation of the structure. So again, this part will not be directly a topic, okay, of the course, but nonetheless, I will provide you with some notes, because eventually we will profit of these, let's say, results, which are relevant in this part, to build upon these results, okay, in the coming part of the course. And so that's why I inserted it, okay, so that we will see that we are talking the same language, okay, with the same expressions. And so you will have this part as a reference. Then we will go through the dynamics of deformable bodies, okay? So in the first part, as I said, we will describe the dynamics of rigid bodies, and then we will add the deformability. And we will see what are the main issues due to this, let's say, double point of view of encompassing large rotations and large displacement due to rigid motion, rototranslations, okay? So we will encompass, we'll be able to describe large displacement and large rotation of the bodies, but then we will also have to deal with the deformability of the body, okay? And we will see that, in theory, this will require an infinite number of parameters to describe, okay, this deformability of the body. So we will undergo some simplifying assumptions. So we will basically do an approximate formulation. And we will be able to encompass also this part, okay? And then there will be the final part of the course, which will deal with mainly, let's say, finite element approach, okay? So there's going to be a numerical part, okay? And eventually, in the very last part, we will see also some ROM models, so it's reducer order models, okay? In order to be able to reduce the number of parameters, we will see that better later on in the course, that we will need to describe a model. So sometimes we don't need the model to be as rich as it is initially, but we can disregard some aspect, and we will see how, in order to have some more, some system, some modelization which is more simple to handle, okay, but which still contains the information which is relevant to us, okay. So this is the very last part. One more thing that will be included in the course will be a cycle of seminars from an expert from MSc, okay, which is Daniele Catelani, you will be able to use the, or at least to be introduced to the use of the software Adams by MSc, which is typically used for the modelization and in general to solve basically multi-body problems for the dynamics of multi-body. There will be 4 lessons, okay, and let's say the dates are still not yet defined, but probably they will be in April, okay. You will be given the details on this as well, okay, later on in the course. I will ask you also to, on this respect, to prepare, let's say, a result. So let's say an exercise will be based on these seminars. You will be asked to do it. And then you will be able to give this result, so this exercise, to me. It's just something that which is not mandatory, but which will save you, let's say, a question, okay, at the exam. The exam will be oral, okay. So the exam will be oral. There will be 4 questions. If you will go through the, let's say, this exercise, this numerical exercise, which will be dealt with during the seminar by MSc, you will save 1 question at the exam, okay? But as I said, it's not mandatory. Yeah, it's here. And you are? Yeah, sure. Okay. I will have to ask you then your name to just to take it to the notes for the epidemic rules, you know. So please have a seat, no problem. Okay, so this will be the content, more or less, okay? Is there any question about that? If not, we can proceed. And so this I can actually also fix like this. Should be okay. It's just a reference, nothing. You will see, you will have this index basically made available already. There you go. It's kind of non-trivial to just handle all of these things. There you go. All right, now it's fixed. So why is it relevant to study multi-body space structure dynamics? Well, there are, several reasons for that, but the main one is that when you place a structure in the space environment, it couples with the space environment itself, meaning that it will undergo different kinds of inputs. And this, let's say, influence of the space environment over the structure is more complicated the larger are the structure. Why? Well, if you take into account a large structure, the effect of these inputs that we will name in a few moments on the structure cannot sometimes be seen as, let's say, constant over the domain of the structure. Meaning that in this case, you will be forced to take into account the effect of the flexibility of the structure. Okay, and the larger the structure, the heavier, the more important are these effects of flexibility. Okay, it is apparent, therefore, that when you deal with multi-body structures, you will typically have to treat larger structure because it's typically composed of multiple bodies and multiple parts, so they will be placed in a wider domain, and so this effect of the environment will influence the system in a deeper way. How? So, well, if you take into account, for example, 2 effects, let's see. So we can call this part flexible multibiodynamics. So let's take two effects of the space environment. So we have, first of all, the coupling with orbital dynamics. With structural dynamics. This coupling is a one-way coupling. What does this mean? It means that typically the position that you occupy during your planned mission will influence the structural dynamics, but not the converse. Okay, the converse is not true. What does this mean? For example, let's take into account the effect of gravity. So gravity is typically described with a gradient. Okay, so we have a gravity gradient, which can be typically written like this. We have, this is the gravity potential UP, and then we have a position over your space system. So RP I and RPJ are basically, if you want, the X and Y coordinates over your body, okay? So if your system is wide enough, you cannot consider the effect of gravity to be constant all over your system, okay? And of course, depending on the position over your, let's say, trip, over your plan, the intensity of the gravitational effect may vary, because it depends on how close you are, for example, to Earth. If you are just considering the gravitational field of Earth. So, in this sense, orbital dynamics, so the position, okay, that will occupy during your plan, will eventually influence your structural dynamics because of what we have said, but the converse is not true. Okay, so of course your structural dynamics will not, in general, be able to influence the path, okay, that you have planned. Okay, so that's why it's a one-way coupling. One-way coupling. Another example through which we see the effect of flexibility, another coupling, is the coupling with the attitude dynamics. And again, structural dynamics. Also, well, for example, let's take into account, for example, let's say solar radiation and solar pressure, okay, solar wind. So, solar radiation and solar wind. So solar radiation is basically the overall radiation from radio frequency to X-ray coming from the sun, okay? While solar wind is actually the overall effect due to particle interaction. So in solar radiation, we are talking about waves. In solar wind, we talk about particles that actually hit, okay, You heat basically the structure. And in this case, we have a coupling, which is not a one-way coupling, but it's a two-way coupling. Why? Because, for example, depending on, let's make this example, depending on the orientation that you have, or let's say a satellite or whatever other spacecraft, okay? Depending on the orientation, the effect, for example, of heating, okay? So you have basically solar radiation will cause an overheat of the structure. You have thermal heating, okay, because of radiation. And this radiation depends on the angle that exists between the solar rays and your surface, which is being heated. So in this case, the attitude dynamics, the orientation or your overall let's say, spacecraft can influence the structural dynamics, inducing a state of thermal stresses, for example. Okay, but again, if the structure is, let's say, big enough, and then we will see what this means, you will have a deformation of the structure, for example, due to thermal effects that can influence also the dynamics, okay? Because the shape is changed due to thermal effects. And since the shape is changed, then you can also have a resulting change in the inertial properties of the structure. And if the inertial properties of the structure change, then you will have to counter this effect for altitude dynamic control. Okay. Why and how can you actually consider this or disregard this? Well, let's say that typically you know that the dynamic of a problem typically are described, at least in the linear part, by mode of vibration. Okay. There is an eigen problem which can be associated to the linear part of a dynamics, okay, of a problem. This is true for the structural dynamics. It's true for every other kind of dynamics. So you can have eigenfrequencies or eigenmodes for the linear part. Well, typically, the frequencies that describe the orbital dynamics and the frequencies that describe the structural dynamics are very, very set apart. Okay, so they are not in the same range. Okay. Typical structural dynamics are in the range, okay, from the lowest, depends on the structure, of course. But you can have something in the range of hertzes for the lowest ones. On the orbital dynamics, you can think about a period, okay, of an orbital mission. The time is not comparable. It's much, much wider. So there is no coupling in this sense. It's only coupling in this way, but not on the other one. Okay, true. In attitude dynamics and structural dynamics, well, attitude dynamics is about controlling the attitude, so it's about controlling the rigid motion, okay, the orientation, if you want, of the spacecraft, okay? While the structural dynamics typically encompasses the flexibility, okay, of the structure. Well, when can you say that there is no influence between the, let's say, the eigenmodes of the structural dynamics and the eigenmodes of the attitude dynamics? When typically there is at least one order of magnitude of difference, okay? And you know that if you think about the structural problem, if the structure is large enough, it becomes less stiff, typically, okay? The larger, the leaner, the lower are the eigenfrequencies of the structural problems. So they become closer and closer to, of course, of what? To the eigenfrequencies of the attitude dynamics, which are, since they are, as I said, associated to rigid motion, they are zero. Okay, rigid motion have an eigenfrequency which is zero typically. So, for example, the spin. Okay, from a structural point of view. Yeah, please.
I have two questions. One, when you say large, that is reference to the
No, as I said, so we are talking about a comparison, for example, in this case, between attitude dynamics and structural dynamics. Okay, so it's not in absolute terms. It's just in comparison the one to the other. Okay, so if you want to let's say, describe your spacecraft as a mere point mass, without disregarding basically its flexibility, there has to be at least one order of magnitude in terms of values, of difference between the modes and the frequencies associated to the structural dynamics to those associated to attitude dynamics. Okay, this is what I'm saying.
This is something that I have trouble with, which is how do we relate eigenmodes
to what?
to attitude dynamics or structural dynamics?
Well, structural dynamics, if you, for example, take into account the linear part, if you linearize the structural problem, you will have the dynamics typically described by the eigenproblem, then you have eigenfrequencies and eigenmodes. Okay, so this is typically what is done, and then you can describe this kind of dynamics like this. It's very easy. Okay, for example, take into account, I don't know, a spacecraft with several booms. Okay, and then, for example, let's say that if you have an eigenmode that is symmetric, okay, for example, let's make a drawing. This. There you go. Okay, so let's consider this. So you have a central part and then 4 booms. Okay, you have 4 booms with an n mass. If you take into account, for example, this eigenmode, which is a symmetric one. Okay, so this is basically breathing all together the system. Okay, this is a symmetric one with a central symmetry. This will not in any way influence the orientation for this simple problem. Okay. In this other case, instead, if you have an antisymmetric deformation, okay, for example, you can consider that these along while these remain still, okay, as an eigenmode. In that case, you will have a perturbation of the orientation. Okay, so you will see that in that case you will have a coupling. So not all the modes, structural modes, can couple with attitude dynamics, but some can, and typically are the antisymmetric one. Okay, they are the most dangerous typically. And in this case, for example, this mode couples with the orientation. Okay, this is a very simple example in the plane. Okay, you're not convinced by that?
This I understand.
Okay.
So the difference is, it is coupling or not coupling. We can tell that by the magnitude.
Yes, exactly. If they are set apart by one order of magnitude in terms of eigenfrequencies, you can describe your spacecraft as a point mass, typically. Okay, so you can disregard the flexibility of the parts. If this is not the case, you cannot disregard the effect of flexibility when you're talking about attitude control of your spacecraft. So you have to consider that it actually deforms under the effect of these various effects that we have named, like gravity. Okay, we have solar radiation, solar pressure. Then there is, for example, there is the magnetic effect. So you know that our spacecraft are typically, if you consider them rotating about the Earth, they are immersed in a magnetic field. Okay, we have also something for this. I'm not sure if you can actually see that. Maybe let's put it here. So this is just a very, let's say, rough and simplified description of the magnetosphere. But again, you see that if you consider the magnetic field, which is typically associated to the currents which are within the electronics, for example, of your spacecraft, they will couple with this. And so again, depending on the position that your spacecraft will occupy on this, you will have a change in the effect. So again, we go again in the sense of orbital dynamics, in this case, coupling with spacecraft structural dynamics, but not the converse again. So what is the sense of all this? As I said, structural dynamics couple typically with other dynamics that involve your spacecraft. And you cannot always disregard the effect of flexibility with respect to this coupling. Okay? There are cases in which you have to take into account this. As I said, the most simple case and the most, let's say, easy to think is the one that I mentioned. So the effect of solar radiation, okay? So they depend on the angle of incidence, okay, over your structure. And so it depends on the orientation of your structure. Again, the incidence with the radiation will hit your structure. Your structure, as a result of thermal stress, it can bend. And this bend will, again, change not only the incidence with the solar rays, and so this is a nonlinear problem, in fact, but we also change the inertial properties of your spacecraft. And again, you will have to take into account this for the control of the attitude dynamics. So all these effects are larger when you take into account larger structure or larger systems of structure, which is the case for multi-body structures. Okay, so multiple parts coming together. So we will see in this course how to relate the dynamics of different bodies conforming to a system, how to describe them in space, how to derive the equations of motion for them for the case of rigid bodies or deformable bodies. Okay. Do you have any question? I would just like to check if you can actually listen to us from home.
Sì.
Okay, thanks. All right, if this is true, then we can start and see how we can describe the position and the orientation of rigid bodies in space, which, as I already mentioned before, constitute the basis of the kinematics of rigid bodies. Okay? Sure.
So, for a given large body, and the relation between solid appliable
Mm-hmm.
that's the radiation pressure, and consider or calculate the eigenmodes,
Mm-hmm.
and then compare them with the structural modes,
Mm-hmm.
and see if they are decoupled or not, and we'll consider only the ones which are coupled.
Well, it's not really like that. Let's say that you, one way to do that is to consider your structure. We will see how to be able to describe the structure in a simplified way so that you can let's say, structure the eigenproblem associated with the structural dynamics of your spacecraft in a simple way. You will see that. You will be able to derive the eigenfrequencies and the eigenmodes. If these eigenfrequencies are at least one order of magnitude apart, okay, typically larger, okay, higher, than the one associated to the attitude dynamics, then you can separate these two problems. If this is not the case, then you will see, okay, which eigenmode is actually entering the red zone. Is this important? For example, if it's the case of a symmetric one, for certain parameters describing the attitude, no. Okay, then you can say, okay, this is a symmetric mode. It doesn't actually influence this parameter, which is governing my attitude. Then I can still say that there is no influence. But you have to search one by one. Okay, you just can't say once and for all that they are decoupled. Okay, or coupled. It depends on the parameters of the attitude control, and depends on the modes, eigenmodes, the structural eigenmode that you are considering. Okay, if there is actually an influence. The one saying that, okay, they have to be one order of magnitude at least apart, it's just a rule of thumb. So let's say it's a very rough way of describing it. But if it's satisfied, you can, let's say, safely say that they are not coupled. If this is not the case, then you have to go deeper into it and actually look at it one by one. Okay? All right. So, as I said, multi-body systems typically can undergo large displacement and rotations. Okay? So we have to be able to describe this large displacement and rotation. How? We first start defining what is called an inertial frame reference. Inertial frame reference is a frame which basically, as we said, is basically fixed in space. So it doesn't move. And we typically, so just as an introduction, I will anticipate that there will be a lot of different names and way of characterizing, let's say, quantities in this course. I will be consistent in that, but please make sure that you have noticed all the different things. And I will understress them during the course, but you will see that the nomenclature, if you want, associated, it's quite heavy, but it's necessary because we will be able to, let's say, differentiate between different quantities, okay, refer to different frames and so on. So please be attentive to that. So for example, I will denote a vector with, let's say, an underbar like this. So this is x1, x2, and x3, and then we have O as an origin. And this is the first frame. Then, since we have multiple bodies, okay, because we are talking about multi-body dynamics, typically what we do to simplify the description is associating a reference frame to each body. Each body has its own reference frame for us, okay? Now we are dealing with rigid bodies, so there is no deformation, okay? All right, so let's say that without loss of generality, we consider a body that has a frame which we will typically refer to as local frame. Okay, the local frame is the frame which is attached to the body. Okay, so for example, if you want, this is my body. Okay, and I describe the body through the use of this local frame, which is attached to the body. In this case, in the case of rigid bodies, it's very easy to say this concept, meaning that the local frame is just attached to the body itself. It doesn't move. There is no relative motion. Okay, so this is very easy. And the definition is very easy because I say, okay, the origin is with respect to the body of the local frame is in this point. It has this orientation, the local frame with respect to the body. I define it at the beginning, and then it stays like that. Okay, so it's very easy. You will see, and we will see actually together, that when we have deformation involved in the process, it is not so easy to define a frame, a local frame for the body univocally. Okay, so in a unique way, because there is a deformation, and then there has to be a relative motion between points of the body. Otherwise, there is no deformation. All right, and in that case, you will see that we will have to make some assumptions in order to be able to define the frame. But this will come later. So the local frame, we call it B1, B2, and B3. It's a right-hand Cartesian frame, as for the inertial one. Okay? All right. Now, how many parameters do you think we need in order to be able to describe this frame, so the local frame, with respect to the inertial frame? Because we said that basically, since there is no deformation for the body, describing the orientation and the position of the local frame or describing the position, the orientation of the rigid body is the same. Okay, so we can say without any kind of confusion, orientation and position of the body of the local frame or orientation and position of the body, because they are attached. Okay, so it's basically the same. So coming back to the question, how many parameters do you think we need in 3D space to define the position and the orientation of the body or the local frame? We do need 6. Why? Well, we call this O prime the origin of the local frame. We'll have Sorry, let me just change a little bit this, just for the sake of clarity. So we have a vector which we typically will define as R, capital R, which define the position, the mutual position of the origin of the local frame with respect to the inertial frame. And these are 3 parameters in space, of course. Then the other 3, we have to somehow describe the orientation of the local frame. Okay, how can we do that? Well, let me just introduce again the frame. Here we go. So you see, we started, let's say, without loss of generality, from a condition which there was just a translation, okay, between the 2 frames, the inertial one and the local one. And then we had a rotation, okay? So if we consider a point P0, okay, in the body, in the rigid body, we typically describe it, the position P0, you see there is no underscore here because it's just a point, with a vector which goes from O prime to P0, which is called R0, which is a vector, with an overbar. So please pay attention to this. We use overbars always to indicate quantities which are expressed in the local frame. Okay? So overbars are typically meant to indicate quantities expressed in the local frame. Because since we have multiple frames, we have to be able to distinguish, okay, in which frame the said quantities are expressed. Okay? In this case, okay, since B1, B2, and B3 and X1, X2, and X3 are parallel in their axis, the components of the frame R0, of the vector R0, are the same. What does this mean? It means that the position of point P0 with respect to X1, X2, X3 is what? Is R, the position, from O to O prime, plus R0. Okay? Is this correct? But R0 with an overbar, the components, if you want, okay, of this vector, are the same both in B1, B2, B3, and in X1, X2, X3, because they are parallel. Okay? So far there is basically no difference, apart from a difference in the origins between the 2 frames. But since the 2 frames are parallel, if I want to describe any vector with respect to B1, B2, B3, or X1, X2, X3, it's basically the same, because the axes are parallel. Okay. Now we undergo a rotation. So if you want, I can replicate this here. Okay. And so we have this R0. This is P0. And then you basically, this P0 goes here, and this is still R0. Okay? This is a very important concept, and we will close the lesson with this, and then we'll continue later on. The quantities which have an overbar, meaning that they are described with respect to the local frame, when you undergo a rotation, they don't change. Imagine that you are on the local frame, that you yourself, you are on the local frame, and you undergo a rotation. Would you notice this rotation? You wouldn't notice anything, okay? That's why R0 bar doesn't suffer any change in terms of its components when the local frame undergoes a rotation, okay? But now I cannot say anymore that the position of point P0 is R plus R0 over bar, because I cannot sum quantities which are described with respect to 2 different frames. Okay. So before I could do that because the two frames were parallel, and so there was no difference. But, okay, in this case, I cannot do it anymore because R0, the components of R0, will not be the same anymore if expressed in the inertial frame. Okay? So I will have to be able to write, instead of R0, this. R0 without an overbar. R0 without an overbar is R0, but expressed in terms of the inertial frame. Okay? What we will have to see is how R0 is related to R. How can I actually describe this with respect to this? You will see that we have to find a rotation matrix, okay? Let's say a matrix that applied to R0 overbar gives us R0 without the overbar. And once we have R0 without the overbar, we can sum it to R, capital R, to obtain the final position of the point. And in fact, obtaining this matrix will signify being able to describe the orientation of the local frame. And we will close basically the problem of being able of describing the position and the orientation of the body. Okay? We will start with that next time.